After exploring lots of videos and articles about P&IDs, we concluded that reading the valve symbols, lines, codes, etc. one by one and memorizing them is the most boring and drying method of learning how to read P&IDs. Stay tuned to the end to tell you why. The sponsor of this video is EdrawMax, an all-in-one diagram software that we are going to use today. And by all-in-one, I mean it. It doesn't matter what your craft is, it provides you with virtually any sort of diagram, chart, or graph you might think of. From basic flowcharts to professional Gantt charts, lean canvas, engineering plans, you name it. And guess what? You can design your process flow diagrams or even P&IDs using its super easy to use interface, countless templates, and an amazing library. Anyways, you can download and try it for free through the links in the description. Before we get started, let's clarify some common mistakes and ambiguities, mostly among students or junior engineers. First off, PID and P&ID are totally different things. PID stands for proportional, integral, and derivative, which are parameters used in algorithms for controlling the process loops. Second, you might hear different extended formats of P&ID, and all of them represent the same document. P means piping or process, but the piping is more common. I stands for instrument or instrumentation. D is for diagram or drawing. Third point is that similar to other documents, like electrical wiring diagrams, P&IDs are typically more than a single page. 4, 5, 10 or more pages depending on the process size, and you only see a specific part of the process on each page. These sheets are usually interconnected with each other. Fourth, there are relevant or maybe close documents to P&IDs that have their own usage, and you should not confuse them with each other. For instance, a piping isometric drawing. It is a sort of shop drawing that is mostly used by piping specialists, and in addition to P&ID information, they include lots of data about fabricating pipelines such as type of fittings, flanges, direction and elevation of the pipes and instruments, and other characteristics. Another fundamental yet related document that P&IDs are actually designed based on that is PFD, or Process Flow Diagram. Here, for example, you see the PFD of an oil and gas project. If I zoom in, you mostly see the major equipment plus some pieces of piping. Now, here is a P&ID from the same project. We have quite a lot more information here in P&ID in comparison with the process flow diagram, don't we? You can think of a PFD as a preliminary version of a piping and instrumentation diagram. So to avoid confusion, a good starting point to read a new P&ID is the process flow diagram if available. Now, let's explore some P&ID examples. This sheet of P&ID is from a chemical process. I have elected this part and manipulated it to essentially emphasize the automation and instrumentation aspects of P&IDs. So you can consider it more of an instrument diagram than a piping and instrumentation diagram. To investigate a P&ID, first, you should know that every company has its own way of illustrating and naming the symbols. They show their symbology methods in detail in some lead sheets called legend and abbreviation, and usually is merely called legend. In this sample of a legend from an oil and gas project, you see countless symbols for primary equipment, instrumentation, numbering and identification methods, piping arrangement, typical details for different instruments, and a lot more. Although the fundamentals of these data are mainly derived from a standard document known as ISA 5.1, and its latest revision was released in 2009. So, to interpret a piping and instrumentation diagram, we have two helpful documents, P&ID's legend and the ISA 5.1 standard. Alright, let's get back to the example. Here, you see a ball mill mechanism The material comes inside the ball mill using a screw conveyor and gets out of that in form of powder. It has a very powerful motor and gearbox to rotate it. There are some utility units like gearbox lubrication and grease unit as well. In large-scale projects, normally, utilities have separate sheets of P&ID, and we will refer to them using these arrows. This is the name, and this one is the drawing number of that P&ID. After showing the main pieces of equipment and piping, the next step is adding the inline instruments. On page 36 of ISA 5.1, we have 16 different types of graphical symbols for illustrating the instrumentation on the P&IDs, and we will explain them one by one. The first and most used instrument symbol is this simple circle or bubble. It's used for physical devices that are installed locally in the field and directly on the main equipment like the variety of sensors or transmitters. For instance, here we have two vibration sensors on this bearing of the ball mill. To identify that it is a vibration sensor, I put the letters VE inside the circle. These letters are corresponding to page 30 of the standard. The first letter is V, which means vibration, and the succeeding letter is E, which means element or sensor. We have other sensors mounted directly on different parts of the ball mill as you see. Generally, these symbols represent a physical instrument or device, and not a computer-based or HMI object. These two symbols indicate physical instruments that are mounted on or inside the main panel, and the other two are installed on or inside a secondary or local panel. If the physical instrument is visible and accessible to us, then we use solid lines inside the circles. And if they are not accessible, we will use dashed lines. You might ask how a local instrument could be invisible to us. Let me explain with an example. We have recently added the Join or Membership option to the channel. By joining the channel, you will benefit from various perks depending on the plan you choose. And at the same time, you will support us to develop more quality videos. You might already know that almost all electric motors have temperature sensors on their windings. As in a normal situation, these temperature sensors are inaccessible and invisible to us. We have to consider a dashed line in the middle of the circle. You might argue that these sensors are not mounted on or inside the panel, so why would we consider a circle for them? I would say that sometimes it depends on the designer how to interpret this symbology. And if they deviate from the standard, they usually mention that in the legend, or they might write a note just beside the page and explain that. According to page 43 of the standard, we can also specify the type of sensor adjacent to its symbol. Of course, it refers us to table 5.2.2. I turn to that table, and under the temperature section, we can see the abbreviation for different sorts of temperature elements. So here, I put an RTD beside the symbols. These RTDs could be directly connected to the PLC cards, but in this case, they have been connected to some transducers within a local box that is stuck to the motor housing. So in the P&ID, we can use a circle with two parallel dashed lines. About connecting the P&ID objects to each other, there is a specific tabular guide on page 46 of the standard. As you see, for electronic signals or electric connections, we should use a dashed line. Thus, I connect all the sensors and their transducers, or let's say transmitters, using a dashed line. I will complete this P&ID in the next video with lots of crucial key points. Until then, please download the ISA 5.1 using the description links and have a look at that. What I'm gonna do now is to draw a simple P&ID using EdrawMax to give you a sense that how easy it is to work with this piece of software. After I open the EdrawMax, I will choose the Engineering category. I click over the Industrial Engineering to explore its subcategories. And here, you'll find the piping and instrumentation diagram. I will click that, and as you see, it shows different P&ID templates. I would rather choose a blank drawing to draw my diagram from the ground up. The first thing that grabs the attention is the pretty complete set of symbols and libraries here in the left area. I just begin with placing the major process equipment and arranging them. So, I open up the Vessels category and will drag and drop a horizontal vessel into the page. The next pieces of equipment I want to add are pumps and their motors. I open the pumps library and select a centrifugal pump from there. I will add another one, and as you see, you can easily align them together. I have added the motors and resized and relocated the devices to find the best arrangement. To add the pipings to our P&ID, you only need to hover the object to find these anchors, and click and drag to another anchor in the opposite object. Or you might want to select the connector tool and click on your intended point, and again drag it to your desired object, just like that. In case you don't need the end arrow, you can easily select the connector and choose the 0 on the end arrow. I have completed all the pipings and added some valves to the P&ID as well. Through this menu down here, I also have classified all the objects and assigned them to different layers. Now, to add some instrumentation to our P&ID, I open up the Instrument menu here. I have a variety of choices. I want to add a pressure indicator right after this pipe expander. I drag and drop it into the drawing and will connect it to the main process line using a connector. I've spent some time completing this P&ID as you see here. In terms of sharing your diagram, you have many choices. You can export it into PDF, PowerPoint, Visio, or even Photoshop or SVG formats. One thing that might surprise you is the wide range of languages that this software supports. And finally, you can use it across Windows, Mac, Linux, or even online. I invite you to download this software through the links in the description and let me know what you think about it in the comments. Hope you liked this video and please stay tuned for the next part of this series.